Okay, chemistry students, we're going to begin lesson 4.2 where we're going to take a look at atoms in the electromagnetic spectrum. And this would go with reading 5.2 in your text. So the objectives for lesson 4.2 are first of all to describe the appearance of an atomic emission spectrum, and we're also going to look at something called an absorption spectrum, which isn't on the objective, but we are going to do it. And then secondly, to explain why and how an element can be identified by its emission or its absorption spectrum. So let's get to it. So this graphic that we have here, and I think I would encourage you to take the time to copy it, and where the text is a little foggy, we'll annotate over it so you can see. It starts with the question, what allows people to make different colored neon signs or different colored fireworks or anything that glows with a different brightly colored light?
Yeah, there were, first of all, a little quick history. There were some physicists who were curious about this phenomenon, and what they did is they passed light from energized atoms through glass prisms in such a way that it caused the colors to kind of break out into their individual frequencies, which is how rainbows form because it reflects through water droplets. And one of the bigger names that you might someday hear from us is a guy with the last name of Balmer. He actually has his own series named after him. The Balmer series is also the Passion series, and I forget the third one off the top of my head right now. Lyman, thank you. But anyway, so
if you just took regular sunlight or like an incandescent light bulb, like in this top picture here, and
you light source.
Allowed some of that light to pass through a prism, you're going to get what's called, if you can read, called a continuous.
What it means is a continuous spectrum.
Spectrum.
White light has all the colors present. It kind of doesn't make sense because you would think that white light would be no colors and black would be the all the colors, because with crayons, when you put all the colors together,
right,
it makes black, not white. But the thing is, black is actually the absence of color or any light whatsoever, right, and white light is the presence of all the colors mixed together.
So if the prism,
we'll separate it out.
We'll separate them out, and then you get your classic spectrum: red, orange, yellow, green, blue, indigo, violet.
So no Roy G. Biv. And if we take a throwback from the last lesson, red will have the lowest energy, longest wavelength, and
lowest
frequency, and violet would have, of course, the opposite of that, highest energy, shortest wavelength.
Out of these colors.
Of these colors, exactly.
Okay, now the phenomenon that leads to like neon lights, people discovered when they said, okay, well, let's just take an element, a pure element, we're going to put it in a tube and pass some energy through it so the gas gets real heated, like it says hot gas over here. And if you look at that light, you don't get all the colors. You only get certain colors. And so this particular gas, we can see we're getting one red wavelength, one yellow-green kind of wavelength, two in the green area, a sort of light blue, and then two up here in the dark blue, indigo, violet area.
Yeah.
This is called an emission spectrum.
And these emission spectrums are like fingerprints for an element or for compounds, because based on the electrons and how they're arranged in the cloud, they give off different colors. And that's going to come up in the next video when we start talking about the Bohr model, his planetary model. This will allow us to understand where we actually get these emission spectrums.
Right, and at first when they discovered this, they thought, hey, really cool, why does it do that? Why do we get just these certain wavelengths of light? And actually, they also discovered another kind of spectrum you can make, which is the one shown on the bottom here. If you pass white light, which we just learned has all the colors in it, through a container of a cold gas, you get what's called an absorption
spectrum, which is the opposite of an emission spectrum. Basically, it's removing the parts that it would emit, which it emits.
And you notice this would be the same element. There's an exact correspondence where we had an emission up here with the hot gas. The same element in its cold state absorbs that particular wavelength. And so why just those wavelengths? Why not, why only just these little handful of wavelengths? And they discovered quickly each element has its own emission spectrum. Like Mr. Hunter said, it's a fingerprint. You can identify the element, but that speaks to the question then, what's going on in the atom that causes it to do that? And that's where our story about atomic structure is going to pick up.
So, yep, let's go on to the next slide. Before we move on too much, let's look at these three elements we have here. We have hydrogen, mercury, and neon. And if you notice, each of the three different the emission spectrums here are different from one another. So to answer the last question from the last slide, how do we make different colored fireworks or different colored neon signs? Well, looking at this, we know they have different emission spectrums, so you just use different elements or compounds to make different colored fireworks. Right. So that's where this kind of boils down to right here. We're showing you three examples.
So yeah, hydrogen has
That's
just
four
a
bands.
few wavelengths there. Mercury's got a few more, and then neon has quite a few. And if you notice with neon, most of its emission bands are up here in the reddish orange and yellow area. And it does have a few down lower on the spectrum. If you ever look at a neon light, these are the ones that look bright reddish orange because it's got this predominance of those wavelengths. When they're all mixed together, your eye just kind of picks out the orange ones.
And then the same, you see hydrogen is kind of like a weird blue teal color when you pass energy through it, if I'm not mistaken.
Because it's kind of you're seeing mainly these three, and there's not as much of that red mixed in.
Exactly.
So down at the bottom, to kind of wrap this up, what we did was showed you an absorption spectrum now, and it matches, it's one of those elements up above.
Yeah, so if you were a scientist looking out in space, this is one way they do things in space, is how they figure out what makes up stars or other parts of space.
We
they
can
use
look at the
emission
emission
spectrums.
spectrum.
So, and sometimes they might get an absorption spectrum. So if you had to identify an element based on its absorption spectrum, you would also have to have its corresponding emission spectrum. So if you're looking at the bottom here and you see there are four, you see there are four bands right here, you would look up here at these three emission spectrums and find which one matches, except for its reverse.
So which one do you think matches, Mr. Hunter?
Well, we have four bands, and this one here has, probably closer to like 12 or 13. This one here has maybe, like 7. And then this one up here has 4. And they're lining up. If you draw your finger straight down, you can see that they line up with one another, which to me would say that our spectrum is probably a hydrogen or absorption spectrum. They're probably looking at some kind of hydrogen.
Hydrogen. Good job.
Yeah. So this is a very basic look at emission spectrums. You will see questions.
We have 2 labs you're going to do too, where we're going to look at some emission spectrum of things, and the colors that different compounds give off in a flame, which will kind of hammer this point home. But we're getting ready now to look at our Bohr model.
And of course, also Study Island will ask questions based on this.
You'll see the diagrams.
So
like
I mean,
this
it's something we want you to be comfortable with, and you're not going to understand why there are different bands until we start looking at the Bohr model. Bohr was the first person to really start looking at these and be like, well, Rutherford has this somewhat planetary model, but Bohr is the one who puts it all together, and he kind of says why this happens. So this video is a lot shorter. We're going to take the difference between this video and the other video and call them both 15 minutes.
All right.
So have a good night, and we'll have some labs about this, I believe, the next day.
Yes.
So see you later.
See ya. So for the post-video questions here, we'd like you to first of all explain the difference between an absorption spectrum and an emission spectrum for an element. And secondly, to give a possible use or uses for these absorption and emission spectra. What could we do with them, or what would be their use to a chemist? So see what you can do with those, and we'll talk about it tomorrow.